So here's another example. Oh, please, quiet down, Drew. Quiet, thank you. Here's another example. Well, I just said we were going to do another one. So yeah, here's another example, and you might appreciate that this is a second order, so you'll get to see how to find the Laplace transform of a second derivative as well. So here's our second order equation: y double prime minus 4y prime equals 6 e to the 3t minus 3 e to the negative t. Y of 0 is 1, we need that condition, and y prime of 0 is negative 1, we need that initial condition also. So when we take the Laplace transform of the entire equation, we get s squared times y of s, remember this is a second derivative, minus s times 1, that's the 1 from here, and then minus negative 1, that's the negative 1 from here. And then first derivative here, so minus 4s times y of s, and then minus our negative 1. And that equals the transform on this side, 6 over s minus 3, and 3 over s plus 1. I guess that's minus 3 over s plus 1. So there we've got that. Now, this needs to be solved for y of s, which is just a big, painful algebra problem. So let's collect up the like terms. This is a s plus 1, so s plus 2, but I have it factored so it's s minus 2 with a negative outside of it. And this is y of s times s squared minus 4s. So I think you see where that part comes in. And this side over here is 6s plus 6 minus 3s plus 9. So that's 3s plus 15 over s minus 3 times s plus 1. And more algebra, we're still trying to solve for y of s, remember, so let's add our s plus s minus 2 to both sides, and then we get this big ugly thing, s minus 2 times this, since I had a common denominator. And so, well, then finally we wanted to divide by our s squared times, or s squared minus 4s. Well, there's the s that I factored out of that, and there's the s minus 4. And so this big ugly thing, which I did multiply out, trust me, I know I probably used the software to do it, but that's what you have to do. You have to multiply this big nasty thing out. I think you can see where there's going to be an s cubed in there, and maybe a I don't know, but trust me, I did that correctly, multiply that out. So there is our y of s. And now, see, we turned the whole calculus problem into this partial fraction decomposition algebra problem. And so it'd be kind of nice to use the heavy side, I think, on this one, since we got all linear factors. So a over s, b over s minus 3, c over s minus 1, d over s minus 4. Great. This is our p of s right here. Our q of s would be what I'd get if I multiplied all this out, and trust me, that's it. And so q prime of s would be 4s cubed minus 18s squared plus 10s plus 12, okay? Why do I want that? Well, I want to know a, and a is p of 0 over q prime of 0, so that's 21/12. I guess 7/4 would be nicer. B would be p of 3 over q prime of 3. Well, p of 3, 27 minus 36 plus 33, so 24. Q prime of 3, that's 4 times 27, that's 108, minus, good gracious, 9 times 18, that's minus 162, plus 30 plus 12, I think you're going to take my word for it, we come out with a negative 12. Again, like I say, you can use this, I use my software, you can use a calculator if you want. The arithmetic does get a little bit tedious, but remember, we're doing algebra, we're not solving differential equations here. Actually, we are. We are solving differential equations, so I'm losing my focus. Let me get back. Okay, I'll go back to try to focus again. C is going to be p of negative 1 over q of negative 1. Well, p of negative 1 would be negative 1, negative 5. I guess that's negative 9 plus 12, so or plus 21, so that would be 12. and q of -1, this would be negative, this would be negative, this would be negative, and that's positive. So we get negative 32 and a positive 12, so negative 20. And d is going to be p of 4 over q prime of 4, and just trust me, 4 cubed minus 4 cubed, that goes away. So 4 times 4 is 16 plus 21, so 37. And q prime of 4, that's 64. Oh, that's awful. There's 52, and 64 times 4. 256 minus 52, and then minus 18 times 16, 4 squared. Well, trust me, you get 37/20ths, okay? I don't necessarily want to do all that arithmetic. I don't think I need to dazzle you with that. Besides, I'd use a calculator, and wouldn't you? So I must have something hidden behind here that's by accident. Maybe it was from me working this stuff out. Let me see if I can expose what I have hidden behind there. No, maybe I didn't have anything hidden behind there, but I do know this. When I get my differential equation solved, I am able to check it. Let me see if I can show you what I did in order to check it. I still need to move this further down, and this is not a text box. Oh, there we go. I got it. There, finally, I caught it. Oh, good. So, we found these numbers, 7/4, -2, and 12/20. I guess maybe that'd be better put at -3/5 and 37/20 for that one. So, our y of s, 7/4 times 1 over s, well, the inverse transform of 1 over s is just 1, so that's 7/4. The inverse transform of 1 over s minus 3 is e to the 3t, so it's -2 times e to the 3t. The inverse transform of 1 over s plus 1 is e to the -t, so it's -3/5 e to the -t. And the inverse transform of 1 over s minus 4 is e to the 4t, and times that 37/20. And we've got it solved. And just for the sake of the argument, let's see if indeed it is the correct solution. So I can take the second derivative of this using my technology, subtract 4 times the first derivative of this using my technology, and look what I get. 6 e to the 3t minus 3 e to the -t, and I hope and pray that that's what the equation says it should have there. So, despite the fact that I think the book answer on this is different from mine, I checked my answer and it's correct. So I do feel good about that. Notice, not only did it save us having to go back and find the constants, it also saved us the torment of finding y of c and then using undetermined coefficients or variation parameters to go back and find the y of p. And so, wow, I mean, there are some really good things to be had for this. Right, nice method.